So we have calculated now or derived the partition function for a canonical ensemble. And we know the kinds of expressions which are possible for a canonical ensemble. Now, using that kind of partition function, now we should be attempting to derive the thermodynamic quantities, parameters for real situations or more kind of practical situations. So within that, the first one we will start with is the most fundamental situation of a classical ideal gas. So let me write down this three-dimensional gas. Three-dimensional gas. I tell you in a moment. So the classical ideal gas, here our aim is to what? First of all, we will calculate the partition function, and then we will try to calculate the thermodynamic parameters. And we know one of the connection equation also, right? A is equal to minus ln qn, minus kt ln qn, right? The minus kt ln qn. So the moment we have the qn, we will get the A and the rest of the thermodynamic potentials through A. So that is the idea. So first and foremost, we will try to calculate the value of the partition function Qn for the classical ideal gas in the 3D situation. So what is the expression which we know if we now need to calculate? In the previous video, we have calculated the expression for Qnvt. Qnvt is equal to integral 0 to infinity exponential minus beta e GD. Let me write it down. Integral 0 to infinity GD exponential minus beta e. Right, this was the expression which we know. Now, with this expression, we should be trying to calculate the partition function for this ideal gas. So which means that now we should be able to tell the number of energy levels or number of microstates which are possible in an interval dE. So if we know that value, then we will be calculating this value GE, right? GED we will be able to calculate if you can tell me how many number of microstates are present in a interval dE. Okay, so now let's take our situation where we have a classical ideal gas contained in a 3D space. I'm very specific in 3D space, which because we will be doing, or I will ask you people to do the 2D case, the situation in a 2D space after this. So a 3-dimensional space, ideal gas is contained over there. Right. Now let me ask you one question. How many microstates are present in a phase space volume, say d omega. So that is a phase space volume d omega, and our task is to find out how many microstates are present in that phase space volume. Now I can write down that expression as the answer. I write down straight away d omega by n factorial h raised to 3n. So this is a three-dimensional space. And the answer for the number of microstates which are present in the phase space volume d omega is d omega by n factorial h raised to 3n. Now let me try to explain you the origin for this expression. I mean, how can one reach this kind of an expression? Now, so in the exam you did not write down that, but for your knowledge, I'm just trying to explain how can one reach that. So for a single particle case, in the one-dimensional case, we know the uncertainty principle, right? What is that? Delta Q delta P is nearly equal to H. And of course, there are, you might tell me that it's S cut by 2, it is S cut, it is S cut. Whatever it is, it's an uncertainty. So delta Q, delta P is uncertain. I fix it as H. Okay. So if we have n elements, so here we are sitting in an ensemble, right? So if we have n elements, in the system which we approximate, the volume around it, for it to occupy, the minimum volume for this n elements to occupy can be written as h raised to n, right? And that also in a three-dimensional space, which means that my particle is, so this was the situation in the 1D, right? In the one-dimensional single particle, this was the uncertainty. So if there are n elements, I should be writing it as, in a 3D space, I should modify it as h raised to 3n. So in there, so my total volume is d omega, and the total volume occupied by all the microstates together in that volume is now h raised to 3n, right? D omega was the volume in the phase space we imagined or started with, and within that volume there are various microstates, and the total volume of all the particles together, of all the microstates together, is h raised to 3n. So therefore, I will write as number of distinct number of distinct microstates in the volume element d omega is d omega by h raised to 3n. Right? Now, during the derivation of the Gibbs paradox for a same situation of the classical ideal gas, we found a fault which we did and we corrected for that. How did we introduce that correction? We introduced a factor of n factorial, right? We divided it by n factorial to account for the indistinguishability of the particles which are assumed in the case of classical ideal gas. Right? We started with a situation of distinguishability, but later we understood that if we have to introduce the concept of indistinguishability also into this situation of classical ideal gas. So we will do that also here. So the expression for this one over here, in that case, will get modified as d omega by n factorial h raised to 3n. Right? There also we divided by n factorial. So now this is what the question which we started with. How many microstates are present in the phase space volume d omega? So that is it. Now the answer is d omega by n factorial h raised to 3n. So that is how we get the expression number 2. I just told you that. So now, based on this one, the expression which we calculated here, we will put this into the equation 1 and modify that expression as QnVT can now be written as 1 by h raised to 3n n factorial integral e raised to special minus beta a. I just forgot the example. And the e raised to minus beta. Since we are now in the phase space, now let me put instead of E, H of QP. Right? Instead of E, I put the Hamiltonian H of QP d omega. So this is the new, the modified expression for the partition function, introducing the value of the number of microstates also. And that means that we just calculated the for the GB. Instead of that, we have put this expression into the phase space. Now we need to see how this energy expression can be written for this kind of a situation, and then we will proceed with the derivation of the partition function in the following videos.